All right, everyone, in this example, we're trying to help design a cylindrical can that is going to hold 12 fluid ounces, or about 355 cubic centimeters. And we want to help design this can so that it uses the smallest amount of materials when creating the can itself. So we're going to have a cylindrical can. It's going to look something like this. And we're going to have to figure out the dimensions of this can. That is, what is the radius value and the height of our can that is going to use the least amount of materials possible. And so we think about kind of our step-by-step process. The first thing we do is identify the objective here. What is our goal? After that, we consider the constraints, what's stopping us from maximizing or minimizing this thing to the extreme. And then once we have that information kind of collected, are aware of all of our knowns and unknowns, we then try to write down some equations that we can use to model our situation. And those are the equations we will be using to find any maximums or minimums of interest. So let's see, our objective here is, well, the volume of the can is going to be fixed, right? It has to hold 355 cubic centimeters. And so what we're actually trying to optimize here or minimize is the amount of materials used to make the can, which is going to correspond to the surface area of the can. Okay, so to help us set up our equation that's going to represent the surface area of our can, we have to think about our constraints. That is, what is stopping us from just making this surface area basically zero or as small as possible? And well, the constraint that we can see right away is that our can has to hold a certain amount of fluid in it, right? The volume of our can has to be 355 cubic centimeters, which is equivalent to about 12 fluid ounces. We also know the volume of a cylindrical can is just the area of its base times its height. So that'll be pi r squared, since we have a circular base, times the height h. And so now we also know, since our volume is fixed to be 355, that 355 is equal to pi r squared times h. All right, so now that we've collected a good amount of information about our situation, it's time to start writing down some equations that we'll use here. We've actually already kind of started that process in writing down this volume equation. That is our constraint equation. Okay, so the other equation we're going to need is for the objective function, the thing we're actually trying to minimize, and that is the surface area. And so what is the surface area of a cylindrical can? Well, there's a couple ways to think about finding it. One is kind of dissect our can and break it up into two pieces, or a couple pieces. Notice that the bottom and top of our can are just circles. So the area of a circle is pi r squared, but we have two of them, one for the top and one for the bottom. So that top area and bottom area of our can is expressed by 2 pi r squared. We then just need the lateral surface area of our can, or the side area of our can. And well, to figure out the side area, we can think about kind of cutting our can along the side or along a seam, and then unrolling it. If we unroll it, well, then it's going to turn into a rectangle. The height of our rectangle is going to correspond to the height of our can, and the width of that rectangle is going to correspond to that circumference of the can. And so what is the circumference? Well, it's just 2 pi times the radius. So that second term for our area equation is just going to be the area of the side of our can, and it's going to be 2 pi r times h. All right, so we're just about ready to start finding the minimum value of this area function. But if we started trying to find that minimum value at the moment, we get stuck pretty quickly because we can notice there are two variables involved in our area equation at the moment, and we don't know how to work with anything other than single variable functions. So what we're going to have to do is put in a little bit more work with our area function and rewrite it as a single variable function. We want this to be an area function of just the radius r, or an area function of just the height h. So we need to eliminate one of these variables, and the way we're going to do that is going back to our constraint equations. Notice in our constraint equation, it gives us a relationship between the height and the radius, and here it looks like it's easier to solve for the height than it is for the radius. So the height is going to be 355 over pi r squared, just dividing both sides by pi r squared to find that. And so that means in our area equation down here, we can replace that h with 355 over pi r squared. And so now it gives us a new version of our objective function, our area function. It's going to look like 2 pi r squared. That first term doesn't change. But for the second term, we can simplify that a little bit, cancel out one of those factors of r. We can also cancel out that factor of pi, and the only thing that's left over for that second term is 2 times 355 in the numerator, which simplifies to 710, and then just a single factor of r in our denominator. So our objective function here is 2 pi r squared plus 710 over r. So now we just have to find the minimum value of this function to make more progress on this problem. All right, so we're at the point where we have our objective function as a function of a single variable. So now we're ready to optimize it. So we have to go through our process for finding these maximums and minimums, and that starts with finding those critical numbers. And find our critical numbers, we first have to look at that first derivative of our function. So if we differentiate our area function with respect to the radius r, we should end up with 4 pi r. And for the second term, we're going to end up with negative 710 over r squared, right? We think of that as 710 times r to the negative 1, and then just use our power rule to find that derivative. Okay, so our critical numbers are going to correspond to where our first derivative is undefined, or where it is equal to 0. And we will get a spot where our first derivative is undefined when r is equal to 0. But if r is equal to 0, that doesn't make any sense in our situation. That would be a can with no volume. So we can actually ignore that critical number right away. So the only critical numbers we're interested in here are the ones that make our first derivative equal to 0. Okay, so to help solve this equation, we need to kind of clear that denominator of r squared. So we have to multiply all 3 terms in our equation, or both sides of our equation, by r squared. Well, 0 times r squared is still 0. 4 pi r times r squared gives us 4 pi r cubed. And then negative 710 over r squared, when multiplied by r squared, just gives us that numerator, negative 710. And so now we can solve this equation in just a few steps to find our critical number r. Right, just have to add 710 to each side, then divide both sides by 4 pi. That would give us r cubed by itself. To really finish this problem off and get our r value, we just have to take the cube root. So r is going to be given by the cube root of 710 over 4 pi, and that works out to be approximately 3.87 centimeters. So one thing we haven't done here, but we're going to skip because I'm running low on space, is we haven't verified that this critical number actually corresponds to a minimum, but we could do that using either our first derivative test or our second derivative test, and technically that is a necessary step that we should be doing. I'm just skipping it here because I'm low on space. So it does turn out that this r value does correspond to a minimum value. So this is going to be the radius length that minimizes the surface area of our cylinder. So remember, the original question was asking for all the dimensions that are required for our can to use the least amount of materials possible or to minimize the surface area of our can. We already found the radius value that makes this happen, about 3.87 centimeters. We still have to find the h value, or the height of our can, that goes along with this radius value. And to find that height value, we just go back to that equation from our constraint that we used earlier. H is equal to 355 over pi r squared. So h will be equal to 355 over pi times 3.87 squared. And that works out to be approximately 7.54 centimeters. We have found the dimensions of our can that are required to minimize the surface area of our can, and therefore use the least amount of materials possible in constructing our can, while making sure the can still will always hold 355 cubic centimeters, or 12 fluid ounces, right? The radius value we found to be about 3.87 centimeters, and the height that goes along with that is about 7.54 centimeters.